here we go. Let's run through this assumed knowledge stuff for area of study 2. So, two measurements of electricity are current and voltage. Let's look at current first. So it says here current is the flow of charges through a circuit and is measured in amps. The definition of an amp is 1 coulomb per second. 1 coulomb of charge every second is the definition of what 1 amp is. So therefore a circuit that has a current of 2 amps flowing through it has 2 coulombs of charge flowing through it every second. One important piece of information that's not on here is what 1 coulomb is equal to as far as number of electrons goes. So 1 coulomb of charge is equal to a lot of electrons. So that is how many electrons are in 1 coulomb of charge. So therefore the inverse of that is 1.602 times by 10 to the minus 19 coulombs. So it's that many electrons make up 1 coulomb of charge. So therefore the charge of an electron is that much of a coulomb. Alright, so voltage is the other measurement, and the voltage is often called EMF, or as I prefer, potential difference, and it's measured in volts. Volts are required to push a current. If you have a circuit and you don't apply any voltage to it or any potential difference to it, you will not get a current through it. The definition of a volt is joules per coulomb. So therefore a 9-volt battery gives 9 joules to every coulomb of charge. So therefore if you were told that you had a circuit and it was a 9-volt circuit and you knew that there was a current of, let's say, 3 amps flowing through it, you know that that 3 amps is 3 coulombs per second, and you know volts is joules per coulomb. If they said, what's the energy flowing through this circuit every second, or flowing out of the battery every second, you would know that you've got 3 coulombs, and each coulomb's getting 9 volts, so it would be 3 times 9, which is 27 joules per second. We'll come back to this. So there's a formula further into this document that represents that. Okay, so this is the mathematical definition of what a current is. What current is? So that's our charge in coulombs, and our time, of course, in seconds. It's always in seconds in physics. We already knew that. So 1 coulomb of charge in 1 second is what 1 amp of current is. Alright, so there's 2 terms for current. So anytime the word current by itself is used, you have to assume that they are talking about conventional current. Conventional current's the flow of positive charge, and it travels from the positive terminal to the negative. So the long bar of any of the battery is the positive. So the conventional current in this circuit is going in this direction here, and that's what this purple loop represents, with I for current here. That, when we're just talking about current, that means conventional current, and it's anti-clockwise. However, actually inside the wires we have electrons flowing, and the electrons flow in exactly the opposite direction. So the electron current is flowing in a clockwise direction in this circuit. So this is what you need to be careful of, is that the conventional current and electron current travel in opposite directions. But if someone's asking you to nominate the direction of the current, if they're just using the word current by itself, you know it's conventional current. If they want you to tell them the direction of the electron current, they need to say electron current. Alright, so current by itself, you have to assume that they're talking about conventional current. Okay, measuring voltage and current. So this is why I think potential difference is a better term. Because when you're measuring voltage in a circuit, you are measuring the difference in voltage between 2 points, not an absolute value of how much voltage a coulomb of charge is carrying. So if you were to set up a voltmeter across this battery here, we know it's a 5-volt battery, so the difference in the potential difference, the electric potential difference, would be 5. The difference between this side of the battery and that side would be 5. So there's a little animation for this circuit. We've got little charges running around and they've got 5 joules of energy. And they go into the first light bulb with 5 joules of energy. They come out with 3. They go in with 5 and they come out with 3. They've lost 2. And that's what you find when you hook up a voltmeter to this light globe here. It will give you a reading of 2 volts because it's always going to tell you the difference, the potential difference. Second globe, they go in with 3, come out with none, and therefore the voltmeter connected across light globe number 2 is going to give you a result of 3 volts. Note that our charges return back to the battery with 0 joules, and charges always return to the power supply with 0 joules of energy, regardless of the type of circuit, whether it's AC, DC, series, parallel, does not matter. And this allows you to determine potential differences in a circuit. So for example, for this situation here, we know the battery's 5 volts. If they didn't tell us how many volts were dropped across the second globe, we could work it out. I know the battery's 5 volts are getting supplied. I know 2 of them are dropped here, so I must know that the other 3 are getting dropped across the only other circuit element here. Right, so I've just repeated this diagram just so I can scribble over here a bit. So this is where people get confused with measuring voltage. If you measured voltage between these 2 points here, this charge is going in with 5 joules of energy and coming past your second point with 5 joules of energy. Therefore, your voltmeter is going to measure 0 volts. The trap people fall into is they think, oh, 0 volts means there is no current flowing, there's nothing happening in this circuit, and that is obviously wrong. So this, I mean, we could have 1,000 volts flowing through here, and at this point it would also be 1,000 volts. And so therefore your voltmeter would show 0 volts even though you have a huge voltage running through here and potentially a massive current. So remember, voltage is just telling you the difference between 2 points. And as you can see, the voltmeter does need to be connected up in parallel, which is what we've got here. So voltmeters always need to be connected in parallel. So if you wanted to find the voltage of this battery, you'd get your voltmeter and you would bridge it like that, making a parallel branch. Ammeters, however, measuring current, have to be inserted in series or inside of the circuit. If you like, you can think of it that an ammeter needs to feel what current is running through the circuit before it can tell you. So you need to put your ammeter inside the circuit. Alright, so that gets us to series and parallel. In a series circuit, there's no branching. So an example of a series circuit would be something like this. I've got my resistor here, I've got another resistor here, and why not just put a third one in, complete my circuit. It's the positive side of my battery, that's my negative, so I know my current is flowing in this direction. And I've got my 3 resistors connected in series. So, if I knew that the current was 2 amps, at this point here, because there's no branching, I know the current everywhere. I know the current flowing through resistor 1 has to be 2 amps. I know the current flowing through resistor 2 has to be 2 amps, and I know the current flowing through resistor 3 has to be 2 amps. And the same in these wires here. There is no branching, so the current in one place will be the same as the current in every place. However, if this was a 9-volt circuit, we know 9 volts will get dropped across this circuit, and if all these resistors were equal, then they would each have 3 volts dropped across them. If they were different, of different value, different ohms, then they would have different amounts dropped across them, but the amount dropped across resistor 1 plus the amount dropped across resistor 2 plus the amount dropped across resistor 3 would have to equal 9. I know that that has to be true. In a parallel circuit, our resistors, or our circuit devices like globes, whatever, branch off each other. And in a parallel circuit, let's again make our power supply 9 volts. In this situation, each one of these resistors would be getting 9 volts. Right, so they each get the same amount, the full amount. However, if our current, again at this point, if our current was 2 amps, the current in here wouldn't be 2 amps. So the current in here is 2 amps, it branches. So the current here would be less than 2, less than 2, and less than 2. But added together, the current in here, plus the current in here, plus the current in here would have to equal 2. So in a parallel circuit there is branching, yes we know. Components on different parallel branches all get the same voltage, so these are all getting the full whack of 9 volts, same as the power supply. But they share the total current. So let's say, what's 2 divided by 3? 2/3, so 0.66 of an amp in each branch. And so really this is what Kirchhoff's laws are, as they're just a, what would you say, a written version of what we've talked about just then, or what I've talked about just then. The sum of electric currents that meet at any points equal to 0, which that means the current in is going to be the same as the current out, so that net difference is going to be 0. So what that means is that the current flowing into a point is the same as the current flowing out of it. Alright, so the current flowing into the resistor is the same as the current flowing out. The current flowing out of this point is the same as the current flowing in. Kirchhoff's second law: in the circuit, the sum of the voltage drops around the circuit equals the total EMF of the battery or power supply. Right, so we know that the voltage drop across here plus here plus here is going to equal 9. Voltage drop around this circuit is going to equal 9. And voltage drop around this one is 9. And this one's 9. Alright, resistance. These are our resistance formulas, but we are familiar with these. So when things are connected in series, you find out the total resistance of the circuit, by adding them together. So it's worth reading this part, that all electrical devices have a certain amount of resistance. Resistance is measured in ohms. The greater the resistance of a device, or the greater the resistance of a circuit, the greater the voltage is required to push a current through it. And Ohm's law shows us this. So Ohm's law is V equals IR, we all remember this. So if you're looking really for a definition of resistance, let's get resistance by itself. Resistance equals V over I, volts per amp. So the higher the resistance, if you want to push 1 amp of current through this circuit, the higher the resistance, the higher the voltage required to push this current through the circuit. For calculating the total resistance of devices connected in parallel, it's this formula, and I just need to make you aware of a mistake that you will never make. Please never make this. Alright, so I'll show you, I'll go through how to work it out and show the pitfall here. Let's consider that we've got 3 resistors set up in parallel with each other, and each of the resistors is, let's say 2 are 100 ohms each, and 1 is 50 ohms. So what's the total resistance of my circuit? Well, we know adding fractions we need the same common denominators, or we need a common denominator. So we need to change this 50 into 100. So if I times this by 2, that's going to give me 100, but I've got to do the same to the top. So what I will have is 1 over RT equals 1 over 100 plus 1 over 100 plus 2 over 100. So 1 plus 1 plus 2 equals 4 over 100. And this is where a lot of people will say the total resistance is 4 divided by 100, and that's not correct. 1 over the total resistance is 4 over 100, so let's flip this fraction. If we do that on the left hand side, we'll do it to the other. (100) divided by 4 is 25 ohms. So the total resistance of this circuit of my 3 resistors connected in parallel, 100 ohms, 100 ohms and 50 ohms, is 25 ohms. And just to make sure, this number you get for the total resistance of a parallel circuit is always going to be less than the lowest valued resistor. So in this case, our lowest value is 50, and it's less than that. Always that number is going to be less than the smallest number you've got in here. Okay, so some formulas. P equals VI, this is our power formula. This is given to you by the VCAA. This one isn't. In fact, there are, I think if you look on last year's mid-year exam for Year 12 Physics, they gave you two, maybe three formulas for this whole area of study. So this is one of them. Ohm's law is the other. So P equals VI. P is measured in watts, and watts literally is joules per second. All right, so joules per second. So a 1 watt is 1 joule per second. So a toaster that might be 2,000 watts, that means your toaster is using 2,000 joules every second. So that means we can understand this formula quite easily. So if P equals VI, that means watts, joules per second, times by time, gives you the number of joules. So pretty simple. So the total energy a device will use, or often in a question they'll say use the word dissipate. The total energy a device will dissipate is equal to the voltage getting dropped across it, the current running through it, times by the amount of time we're considering. I'll, instead of going to the next slide just yet, you can see that VI is the same as P. So this formula can be rewritten as E equals power times by time. All right, it's exactly the same thing. And that's what is on this slide here. So again, a derived equation, so it will not be given to you on a formula sheet. And finally we get to Ohm's law, V equals IR. And by combining V equals IR and P equals VI together, what we can end up with is two different versions of power formulas. So we've got a formula here that we can use when we don't have a voltage value. So we've got current and resistance, and we can still determine power. And conversely, when we don't have a value for current, we can get away with it by using this version of a power formula. What this does is it can save you a calculation when you're considering a circuit. Instead of going, oh, I need to calculate the voltage and then determine the power, you can shortcut it. And then the same here. If you don't have the current, you don't have to calculate it, and to calculate the power, it can save you one calculation, which is always a good thing in an exam. Obviously, these are derived equations and will not appear on a VCAA formula sheet. Finally, alternating current in comparison with DC, direct current. So coming out of the power points in your home, you have alternating current. And what that means is that the voltage is oscillating between a positive value and a negative value. So oscillating means switching or flip-flopping, toggling, whatever you want to say. So it's going from a positive voltage to a negative voltage, negative voltage. Whereas DC, such as what comes from a battery is a source of DC power, just gives you a constant. So we've been talking about 9-volt batteries with this presentation. If this was a 9-volt battery, this line here would be giving a voltage of positive 9 constantly. In Australia, our AC power supply is rated at 50 Hertz. So when you buy a TV or an electrical device, you'll see it rated at 240 volts, 50 Hertz. And so that's made for Australian conditions, which means the AC signal is flipping from positive to negative 50 times every second. All right, so it's going. So really, when you've got a wire or a cord coming out of the wall, you don't just have a current running constantly in one direction in your power cord. What you have is the current flip-flopping, oscillating backwards and forwards 50 times a second. And what you'll discover in Unit 4 Physics is, even though we call it 240 volts, that does not mean that these peaks are at positive 240 and negative 240. In fact, the voltage out of an Australian power point goes from positive 340 to negative 340 volts. But we will discover the reason behind that in Unit 4. Okay, so finally I have some questions that I want you to do, 8 questions that I want you to do in relation to this presentation. I think I've given away the answers to probably the first 7. Question 8 you've got to go out and find for yourself. So do your homework and then make sure you enjoy your holidays. See ya.